this topic is one of the more prevalent point-wise topics on the AP exam than what we've kind of seen. So units 1 to 4 were both in like that 10 to 12 zone. Unit 5 starts at 15 and goes to 18. So unit 5 makes up almost 20%, which is a fifth of your exam. So this is a very important topic in terms of where we're going, what we're doing, and what you're going to see. So unit 5 involves all of our theorems. Intermediate value theorem says that if you have a low point and a high point, or a high point and a low point, the order doesn't matter, that you are guaranteed all points in between. What someone here learned is it doesn't mean that points can't exist outside of that region. So just because this graphical example only shows the graph between this y value and that y value, it doesn't mean that it doesn't do this. We have no idea what it does. All we know is that it does hit every point between them. It doesn't mean that it can't hit points outside of them. So you have to be cautious about that and use words like may exist, but not guaranteed. So it says a real-world example of this theorem would be to track the temperature of ice cream as it melts. If it takes 10 minutes for the temperature to change from 32 to 70, the temperature of the ice cream must hit every temperature in between. NVT. If you are going to reference or use the mean value theorem, you must, in your justification, use something in the lines of differentiable and continuous possibility. Differentiability implies continuity. So if in the problem they tell you it's differentiable, you are guaranteed continuity. Continuity does not guarantee differentiability. So NVT guarantees for a function f that it's differentiable over an interval and that there exists a number c on that interval such that f prime of c is equal to the function's average rate of change. Remember, this says that instantaneous equals average. IVT guarantees that instantaneous equals average, or that slope of the tan equals slope of the secant. Another way to think of that is to say that the tangent and the secant will be parallel at some point. I feel as though recently they said, when will these graphs be parallel? They throw that parallel at you and you guys go, ah. So you would think of the derivative as being one slope and then use the secant line to find the parallel slope. Why differentiability over an interval is important. So again, differentiability implies continuity. Differentiability also implies a derivative. So if it is not differentiable, then you cannot guarantee that the slope of the secant and the slope of the tangent will equal each other, because this does not take on every slope. So you can see over in that example, that tangent line only has two possible slopes, never being parallel to the secant. Does NVT apply to function h? Over the interval -5 to -1. So this is like that multiple choice question that sets you up for failure. Because you see this, and you go, ah, no. But is that sharp corner in the interval they gave me? Ooh. However, what is in the interval they gave me? So if a function is not continuous at a point, that is therefore also not, it's not differentiable or continuous, can NDT be applied? So we have jump discontinuity at -3, which means it isn't continuous, therefore let G be a differentiable function. And G is differentiable, therefore G is continuous. Is there a number C in the closed interval? So we're going -5 to -3 only, such that G prime of C equals -4. So what that means is I am looking for 2 points to equal -4 when I find slope. So you only have 2 potential opportunities, really. You can find the slope of -5 and -4. You can find the slope of -4 and -3. And you can find the slope of -5 and -3. So even though the interval is -5 and -3, it doesn't mean that that's what you have to find the slope for. So maybe you start with that though. So maybe you start with G of -5 minus G of -3. Then you do -5 minus a -3. You get -4. Yep. All right, good. Because the slope of the secant is equal to -4. Therefore, by mean value theorem, the slope of the tangent must equal -4 at some point because the function is continuous and differentiable. EVT appears in tons of free response questions, often as the candidates test. We often use it to determine an extrema. So EVT, I always stress, says endpoints and all the points in between. So think EVT endpoints. The EVT theorem says that if a function is continuous, then the function must have at least one max and one min on our closed interval. And the reason that E is endpoints is because it's on a closed interval, and the max and min can occur at an endpoint. We find our extrema by finding the absolute max or absolute min, by finding our critical points. Our critical points occur when our derivative is 0 or dne, or sometimes they occur when like 2 of the derivatives are equal to each other. Because a lot of times they have to take it one step further and we're finding the max or min of 2 related rates at the same point. So that's when their derivatives equal each other. So an infamous, which of the following is true type questions. So f is a function with the selected values in the table. Which of the following statements must be true? So statement 1, by the intermediate value theorem, there is a value c in the interval 0 to 3. So that means we're looking at f of 0 and f of 3. By the mean value theorem, there is a value c in the interval such that f prime of c equals 2. So again, f of 3 minus f of 0 over 3 minus 0. By EVT, there is a value c such that f of c is less than or equal to f of x for all x in the interval. So make it A, B, C, D, and A. It did not. That's why I never marked or said and indicated. So I showed the work, but if you reread F, it says the function has the given gamma values, but it does not tell us if the function is continuous or differentiable. Therefore, A. Crazy, right? Tricky. So I like that question. It's so hard. Like I was sitting here going like, don't say it, don't repeat it, like, because I wanted to be like, is this true? But I knew in order to ask you if it was true, if you said yes to me, that I would have to show you. But so I was like waiting super patiently. Finding the absolute extrema on a closed interval. Let's find, for example, the absolute extrema of blank. So, apparently all my work just popped up and I can't find it. First thing you would do is find h prime of x. In order to find your absolute extrema, you need to find the critical points of the derivative. So we're going to find our derivative, find the critical points of the derivative. In this case, the critical points are -2 and 1. And then once we have our critical points, we need to know what is happening around them. So we're barricaded in by -3 and 3. I have critical points at -2 and 1. So what that means is if you wanted to find the absolute extrema, you would have to check 3, -2, 1, and 3 in the original. Assuming my critical points are max or mins. So that's why you would kind of quickly check their signs. So -3, you have -3 plus 2, so that's negative. Negative here, 2 negatives make a positive. times a positive, so that's a positive. Plugging in 0 to the derivative, you get a negative. So that means that this goes from increasing to decreasing. So that means that -2 is a potential max. And then if you look at 1 plus 2 is 3, positive, positive, 1 minus 1, oops, sorry, yeah, 2, positive, positive, positive. So that means that at 1, this is a potential min, because it goes from decrease to increase. So again, you can kind of see like that cubic behavior of this function. So to find our absolute extrema, we have to check all 4 points. So 3 would be my absolute max, and 1 would be my absolute min. First derivative test is a way to analyze functions using their points. A point on a function when the first derivative equals 0 or fails to equal 0 is called a critical point. And then critical points are local extrema. And again, we saw that in that previous example, right? We saw that -2 was a local max, but not the absolute max. Because again, the original function is cubic. We know the cubic is odd, which goes in opposite directions. So unless that interval was smaller, -2 was not going to be an absolute max. Find the relative extrema of the following points. So to find the extrema, step 1 says find your derivative. So some Hody Hi minus Heidi Ho. So you should get x squared minus 2x over x minus 1 squared. To find your critical points, you set the derivative equal to 0. So when you set the derivative equal to 0, you have to set both the numerator equal to 0, because that's where the derivative will equal 0. And then you also set the denominator equal to 0, because that's where the derivative will not exist. we end up with 3 critical points. 0, 1, and 2. To use those critical points, we do our number line test. Remember that every time we talk about a function, we must reference f or f prime. If you reference f, then you would say increase and decrease. If you reference f prime, then you would talk about positive or negative. So going back to that second problem or example we were just looking at, we already found our critical points. Now we want to analyze them. So we don't really analyze in a table, that's Khan Academy. We tend to analyze on a number line. So we would plug in something smaller than 0, maybe -1. What's nice about analyzing this is what do you know about, my derivative. What do we know about the derivative's bottom part of the function? Anything squared is always going to be, yeah, so we only have to talk about the numerator when we talk about our sign changes and our points. So we're only concerning ourselves with x squared minus 2x. Because the bottom is always going to be positive. So a negative squared, positive. A negative times a negative, positive. So that's how you know that's positive. Then you pick something in between them. So that 0.5, well 0.5 squared is going to be 1/4. 1/4 minus 1. 1.5, well 3x squared is going to be 9/4, and then 3x times 2 is going to be 3, so 9/4 is 2.25, which is smaller than 3, so negative. That means that even though 1 is a critical point, 1 is not what? It's not an extrema. So this is kind of like where your graph goes increasing, decreasing, and it has like that blip in it, but it keeps decreasing. And then it's going to increase again. Or what actually happens at 1. 1 is a horizontal. Just look at your denominator. So we actually can't even live at 1. So again, that's interpreting the graph and taking into account all those points. Since f increases before 0, it decreases after it decreases after 2, it increases. So that's kind of like the numerical. F is undefined at x equals 1. That's what we just talked about. It's that vertical asymptote. So it can't have an extrema. Concavity. Concavity is our smile or our frown. And again, the table kind of tells you exactly when or where things are occurring. So if it's concave up, it'll be positive. If it's concave down,